Okay, so this video is on the pH scale, and where that comes from is from the auto-ionization of water. So this is called the auto-ionization of water. Means it does it all by itself in pure water, okay? So some water molecules will bang into other water molecules, and when they do, some of the water molecules will lose an H, become a proton donor in Bronsted-Lowry definition, and some will become the proton acceptor. So one of these water molecules was an acceptor and became H3O+, and the other became OH-. It'll also be written sometimes just water splitting to H+ and OH-. The important thing is the L's and the AQ's here, because the actual expression for the equilibrium constant here will just be H3O+, or H+, they're synonymous, and OH-. Now, in pure water at 25 degrees Celsius, right, at 25 degrees Celsius, this is equal to 10 to the minus 14. The other thing important is that in pure water, the H3O+, the H+ concentration, is going to be equal to the OH- concentration. So we can call them both X, which means essentially X squared, which is OH- times H+, or OH- times H3O+, equals 10 to the minus 14. And this is where the pH thing comes from, because X is then equal to 10 to the minus 7. And what that means is essentially that the pH is, what all the pH is, now, I always say it's the power of the hydrogen ion concentration. That's not really what it stands for, but that'll help you remember it, because really, it's the negative log of the H+ concentration, which in this case, okay, is just, I'm going to erase that and replace it, is just 10 to the minus 7. Now, the log of 10 to the minus 7 is minus 7, but if you negate that, you get the value of 7. And that's the pH of neutral water. And it's only the pH of neutral water if it's 25 degrees Celsius, because the value of K will change with a different temperature, and you should be able to adjust to that if you need to, okay? Now, there's some really simple relationships here, okay? So let me rewrite that KW. So here's the idea. The H3O+, okay, times, I'm going to make a little space here, so a little space in the diagram, there's a dot there, okay, times OH-, okay, is equal to 10 to the minus 14. As long as it's 25 degrees Celsius, right, that's really important, okay, because it can vary. And what this means, if you take the negative log of this value here, that gives you the pH. Okay, and if you take the negative log of this value, okay, that gives something called the pOH. Now the cool thing is these guys always add up to the same number. If you think about in our neutral water, okay, the concentration of H+ is 10 to the minus 7, and the concentration of the OH- is 10 to the minus 7, and the negative log of both those numbers is 7. So they're always going to add to the value 14. Okay, and so if, let's say, the pH was 1, right, that's a pH, then the pOH would be equal to 13, because they add to 1. All right? Now, you can go backwards from the pH of the pOH to the concentration, right? So you can go this way, right? And in this case, right, so the pH is, let's say, you go back from there, you basically, it's 10 to the negative pH, right? Or, or 10 to the negative pOH. Now let's do a pretty simple problem here, okay? One in which we have a strong acid, because that makes it easier too. So let's say you have 0.02 molar HCl, right? And you want to figure out what the pH of that is, right? Well, since HCl is a strong acid, its equilibrium point lies way to the right. You could do something with the K, but you don't bother here because it is sort of like a salt that completely dissolves, right? So if every one of these, you definitely get one of these. This would not be true for a weak acid. So we can assume that the H+ concentration for this strong acid is equal to 0.02 molar, right? Now, what I can do now is I take out my calculator. So what I do now is I can take out my calculator and I can take the negative log of this value. So if I do negative log of the 0.02, the number I get is equal to 1.69. And what that means is, okay, that's my pH. Right? Now the idea is if there's more hydrogens, there have to be less hydroxides because they still have to multiply out times 10 to the minus 14, right? So, I can have a situation where, if the pH is this, then the pOH, right, is equal to 14 minus that number. So I can, subtract 14 from there, right? And what that tells me is the pOH is 12.30. But it also tells me the hydroxide concentration, right? No, these two numbers add up to 14 every single time. So I can basically 10 to the negative 12.30, and I can find out what that stands for. And when I calculate that, by the way, is my hydroxide concentration, right? And that's equal to 5.01 times 10 to the minus 13. And this, is legitimately the answer, honestly. I don't know why someone would complain, but if they asked you for it in scientific notation, you'd have to do this whole little thing here to make it legitimate, okay? So that's the pH scale. One thing you want to recognize is that the kW does change, okay? So if you go to, let's say, a higher temperature like 50 degrees Celsius, the kW will be a larger number. And that means that it causes a shift to the right, okay? That means this way is endothermic. So you get a larger value, which means the H plus and the OH minuses are different. And I'm not going to do the math here, but I'd like you to try it. It's on one of the worksheets. And when you do this, when you try to figure it out, if they tell you what if they say it's, if you do 0.02 molar HCl, H plus, and you plug that in there, they don't multiply out to the same number, so you get a different value for the hydroxides, okay, and a different value for the pOH, and a different value for the pOH as well, because they don't add up to 14 anymore. They add up to a different number. I'll stop there.